Alright, so question 8. A scientific survey of shark species in the Great Australian Bight recorded an average length in centimetres and the average weight in kilograms. I always take these down because they're useful to find the units. Of 10 species of shark. The data is shown in the table below. Both a linear model and exponential model is found for the data. A residual plot, so these are residual plots, not the actual graph. Regression equation and coefficient of determination. I might actually just highlight residual plots, so I remember that. For both the linear model and the exponential model are given below. Excellent. Using the information above, explain why the exponential model is more appropriate. Okay, so the exponential model is more appropriate to use in predicting from the data in the table. So the first thing I'm looking at, because it's giving 3 different things, you're probably going to be, well, they're probably expecting you to refer to multiple things here, not just one. So the first thing I can see here is the exponential model's R-squared value is significantly closer to 1. So that'd be the first thing. And then the residual plot itself is probably the other thing they want you to see something in. So you're probably looking one or two things, looking for a pattern or looking for relatively small numbers, residual values. Looking at the residual values, they seem to be fairly comparable. So I think it would be the pattern that they're sort of seeing here. It's starting the positive, moving to the negative, and then moving back positive. You can nearly argue there's a pattern here, but it's not as obvious. So yeah, I think it's a pattern and the R-squared value is the 2 pieces of information. So the R-squared value for the exponential model is significantly closer to 1. Than the linear model. And the linear model also has a pattern in the residual plot. That starts in the positive, moves to the negative, then moves back positive. So I think that's really what they're probably looking at, is multiple things that you're wanting to state there. You probably want to make reference to the residual plot as well as the R-squared value to get both your marks. That's probably what's quite important. Alright, so identify a possible outlier in the data. So the outlier I can see is this one just here. You can see it in both really. So what you're really wanting to come down and have a look at is where the length is. So the length is somewhere between 150 and 200, closer to 200, probably about a 180 somewhere. You're wanting to see somewhere in these 180s, somewhere that's just way out there, and you can see it's just here. It's that 186, 141. So it's that 186, 141. That is the possible outlier as a coordinate. The outlier you identified in part B was found to be a recording error. Remove the outlier, write the new exponential regression equation and recalculate its coefficient of determination. So that's where you want your calculator out again. And in the stat menu, if I was doing this as a proper exam, I'd probably leave those 2 there and start using list 3 and list 4. So I've got this set of data as well as the question set that I had earlier from it. But for now, I'm going to clear these sets. And let's plug these numbers in. So that's my X, isn't it? Yep. So 111, 118, 129. Be extra careful when you're doing this. 151. I am going to highlight the one that I don't want to put in. just because that's the outlier. So what was I up to? 151, 162, 172, 185, 190, 201, and then on the Y's, 15, 22, 25, 44, 69, 63, 83, 99, 122. Stat, we want to calculate, what are we calculating here? The exponential regression model. That's the one that's just here. X was list 1, Y was list 2. Let's calculate it. So you can see here, write the new exponential regression equation. So we want to write this in terms of W and L again. W was my Y, so this will be W equals my A value of 1.48, let's say. They go to, 1.48 multiplied by my B, so multiplied by 1.02. Let's go to the same decimal place they did each time. And I'm going to say approximately 2 to the power of L. Alright, and its coefficient of determination, so R squared is approximately equal to 0.975. So you can see here that's gotten closer to 1, which is what you'd expect if you're removing an outlier. Alright, so moving on. A shark has been caught in the Great Australian Bight. And scientists think it's a new species. The length of the shark is 100, so the length is 143 centimeters. Using this length and exponential regression equation you found in part C, predict the average weight of the new species of shark. So, this is the part. I don't like that. Found in part C. What if you didn't find it? Oh, I guess if you didn't find it, you could use this one, but it's saying found in part C. I don't like how that question's written. Anyway, I'm not going to pick on the exam question. So what I want here is to substitute 143 for my L. So my W is going to be approximately equal to 1.48 multiplied by 1.022 to the power of 143. That was in centimeters, wasn't it? Excellent. And then you just chuck this in your calculator. So 1.48 times 1.022 to the power of 143. So therefore the weight will approximately be equal to 33.2, and that was in kilograms. Alright. So state why the prediction made in DI may not be reasonable. Whoa, is it extrapolation? What am I looking for here? The length. So the length was 143, which was not extrapolation. So 143 was interpolation. Alright, so, and it's got a high R squared value. So mine might not be reasonable. Let's actually look back at the original stats. What were they taking? A scientist survey of shark species in the Great Australian Bight recorded an average length. Average. That's what we're missing. Alright, so let's explain this. You've got one shark. You found this one shark. And you've got this model that you've come up with based on averages over a period of time. The issue with using averages is averages are really susceptible to outliers and things like that, which can significantly change things. And if you've got one species, like one sample of data, and you're comparing it to an average model, it's not really worth it. So it's not going to work too well. So what would I say is the correlation found is for the averages of how many species of shark? 10. Oh, but we removed one. So 9. So I have 9 species of shark of shark, not from individual sharks, so not from individual sharks. Using a species average, without knowing sample sizes. I'm actually going to write that as well. So without knowing sample sizes, we'll say also without knowing sample sizes, knowing because that can have a bigger effect as well, because remember, averages are... Okay, I've just realised that my face cam has just turned off, but that's all right. We'll work without the face cam for the moment. I don't know when that turned off. Oh well. So using a species average, also without knowing sample sizes, because remember, sample sizes are significantly affected by... outliers significantly affect averages, so a bigger sample size will reduce that effect. But anyway, using a species average, also without knowing sample sizes, to make predictions. You're writing a lot for 1 mark. Predictions for one individual shark would not be appropriate. I'm sure that is more than enough to earn that 1 mark. But yeah, I think the key there was realizing when I get these sorts of questions about it being reasonable or not, the first thought I'm always looking at is interpolation and extrapolation of data. If it's interpolation of data, that is more reasonable. If it's extrapolation of data, it's not. The fact that this was interpolation meant that it had to be something else. In this case, it was the fact that you were using an individual data point to compare against an average. And that's really what it's probably after there. Or at least that's what I think it was after.